Hi everyone. In today's tutorial, I'm going to show you how you can import any 3D dataset as a numpy array into Blender and display it as a volume object. So I was recently going through the release notes for the upcoming Blender 3.5, and if you scroll down to the Python API and text editor release notes and scroll all the way to the bottom, you'll see that the Python module openvdb is now bundled with Blender version 3.5, and this now makes it possible to import a three-dimensional array containing any sort of data, convert it to a volume object, and display it and render it in Blender. So depending on when you watch this tutorial, you're going to need to download Blender version 3.5. At the time that I'm recording this tutorial, we're currently in alpha, so you need to download this Blender 3.5 alpha version here. So to start off with, we're just going to create a few simple examples just to demonstrate this workflow. So each of these examples requires the new pyopenvdb Python module, which now comes pre-packaged with Blender 3.5. And to enable this Python module, it's just a simple matter of going import pyopenvdb. And because it's pre-packaged, we can just use that simple command to enable it. For this tutorial, we're also going to need the standard Blender Python modules, and we're also going to need numpy, which I've imported as np, so we can refer to this as np wherever we use a function. So for this first example, I'm just going to create a volume, and this volume is going to have side lengths of 20 pixels by 20 pixels by 20 pixels, so it's just a cube with this number of voxels, and I'm just going to use the numpy.random.rand function to randomly assign values between 0 and 1 to each of these voxels. So this is going to create some sort of noisy volume. Once it's created that numpy array of random values, we're then going to create a volume which can then be rendered in Blender. So the first command we have to take from the openvdb module is this grid equals openvdb.floatGrid. So this is going to create an empty volume grid, and it's going to assign float precision to this. But you can also change this float to double grid if you need more floating point precision. Then we're going to use this grid.copyFromArray function, which allows us to copy the values from our numpy array here in our volume to the volume grid. So it's just a simple matter of going grid.copyFromArray, and we refer to our numpy volume here, and I'm casting this to a type float. Next, you can create an arbitrary transformation, and this means like a translation or a rotation or a scale. Here I'm just using the identity matrix, which means no extra transformations being applied, but you could apply, say, an X transformation by changing this value here, or you can adjust the scale by changing these diagonal values. If you're interested in changing any of these, have a look at affine transformations on Google and you'll find out what values to change these to do rotations, translations, and scale. The next step is to change the grid class. So grid.gridClass equals the openvdb module grid class and set it to fog volume. This will work for pretty much any kind of data set you are importing. And then finally, we need to change the name of the volume grid to density so that we can refer to the density attributes in Blender and change the render properties. So you just go grid.name equals density in inverted commas. And finally, we can write out that VDB file, which we can then re-import into Blender by going openvdb.write. The first parameter in this function is the file path to save the VDB file. In this case, I'm calling it randvolume.vdb. And then the second parameter in this function is grid, which is just the name of our grid here, which is containing our volume data. And so this saves a VDB file, which you might be used to just importing by going Shift A, volume, import openvdb. But we're going to do it using Python. And the last step of this code is just to go and find the VDB file that we just saved and re-import it into Blender as a volume object. So you just go bpy ops object volume import, select the same file path as the one we saved it to, this one here, and you just need this files equal empty parameter here. So let's run that and see what happens. So that was pretty quick. You can see we've got this cube here, and you can see on the edges here we've got some sort of randomization. It kind of looks like noise. Let's just drag this over and render it. And you can see there's nothing there at the moment. But if we go over to our shading tab and create a new shader, let's just center this here. You can see it creates a principled volume by default. If I go Shift A and search for a volume info node, because we named the volume in the VDB file density, or the density attribute, we can then use this density property here to control the appearance. So I'm just going to put a color ramp in here as well. Connect the density to there, and the color I'm going to connect to the emission strength and the emission color. And I'm going to set the density to 0. You can set the density value based on this color ramp here and turn the emission off. It just means that you'll have to place lights within the scene to illuminate the volume. But for this example, I just want it to self-illuminate, so I'm going to use the density value to control the emission strength and color. So let's render that now. And that's looking a little bit more interesting, but if I drag this slider up here, you can see I've kind of got this interesting noise pattern, kind of similar to what you would get if you just connected a typical Blender noise texture, 3D noise texture to a volume. But you can do that programmatically with Python now. So that's kind of cool, and I can drag all these up. I could even change the color if I wanted to. Okay, so I'm just going to delete that now. Go back to scripting. Let's have a look at this second example here. So I'm just going to comment out that first example, and I'm going to uncomment these functions. So this will be a little bit more interesting. So in this one, I'm going to create a new volume, and I'm going to use the numpy zeros function to create a empty numpy array of zeros with dimensions 30 by 30 by 30 voxels. Then I'm going to override some of the values in that volume. In this case, I'm going to override the x values of all x values between 20 and 30, all of the y values, and any z value equal to 2, and I'm going to assign it a density of 0.5. I'm also going to override the density of all x values with y values equal to 20 and z values between 10 and 15 to 0.5. Then I'm going to assign the volume x values between 5 and 10, y values with values between 5 and 10, and z values between 5 and 10 equal to 1, so twice the density of these other regions. And then I'm going to do something similar for x, y, and z values between 15 and 20. I'm going to assign that a value of 10. And then we can just leave all this code down here exactly the same, because I'm just controlling my initial numpy array. And these numpy arrays can be set in any number of ways. So you can import scientific data, for example, that you might have in three-dimensional numpy format. But this is particularly good for add-on developers because you can develop these customizable volumes using Blender's scripting language. So let's run that now and see what happens. So again, you can see this empty volume here, but we can't see anything until we go to shading. You can actually see it here in the viewport display, but I'm just going to assign it the same material again and render it. And there you go. You can see we've got these squares that we've got here floating in the foreground. So these are the squares that we assign values, density values of 1, and these planes here have a density value of 0.5. And you can see that just by adjusting this color ramp slider here, so you can see these have got a lower density than these ones up here. So that sort of just shows the power of being able to programmatically or procedurally generate these arbitrary volumes and import scientific data, for example. And for the last example, I'm just going to delete out that volume, go back to scripting. So I've got a slightly more complicated example here. I'm going to show you how to import a medical image. So in this directory here, I've just got a series of MRI images. So typically MRI images are saved as DICOM format, which is a standard medical image storage and communications format. And the way MRIs and CTs are stored is that they are sliced up into 2D slices, and you have these individual files which represent the individual Z slices, for example. And when you stack all of these together, you get a three-dimensional array, which can be displayed as an MRI set. So I've just written this script here to load in all of those slices from that folder. It sorts them by their instance number so that they're correctly ordered, and then stacks them all together, does some scaling because the volume is non-uniformly scaled, and then it uses something similar with the openvdb code to display it in Blender. So I won't go into the details here, but you can use this if you want to, if you've got a medical image you want to display. So all this does is just brings in and stacks all those individual slices into a three-dimensional array, and then it normalizes that array so that we've got density values between 0 and 1. And all this is an arbitrary numpy array. And again, we're doing something similar, except this time I'm creating a double grid rather than a float grid, because I just want that extra floating point precision. And for this one as well, I needed to change the linear transformation slightly because the MRI volume has non-uniform voxel sizes. So I have to scale the X direction by the slice spacing. I'm also converting the units here. So I think it's in centimeters and I needed to convert it. This is what I got. I needed to adjust the scale in the Y direction and adjust the scale in the Z direction. But apart from that, everything else is the same. So I'm just going to run that now. It might take a few seconds longer. And there it is. So if I view and go frame selected, you can see I've got that MRI volume in there now. And I'm just going to, let's see, rotate the X by -90. Just drag it up a little bit. And if I go render, again, we see nothing. So if we go back to the shading tab, let's try, I've got a material here already. Here we go. Let's go view frame selected again. Just drag this down and press render. And you can see we've got this nice three-dimensional render of this MRI data set. And I've set up this special shader just for this particular example, and it allows me to limit the range of the slices. So this slider here allows me to bring in the slice thickness, and from that I can use this slider and I can scroll through the slices. Let's make that maybe 0.1. I can drag this across, and let's turn up the brightness a little bit so you can see. There you go. So now you can see in this particular slice, we've got the brain here, the brain stem, sinuses, nose, and I can scroll through with this one and I can see different parts of the MRI scan, which is pretty cool. And you could also change this around so you can adjust the direction. So I could plug in that to there. Just cancel that, plug that on there. There you go. Now I'm slicing through a different axis now, so I can scroll through. And there's the brain and various other organs. There's the eyes. So again, I'm just using the density attribute to control all of these. I'm also using a texture coordinates node, just so that I can sort by the various axes, so I can display the different planes. And then I can just increase this back up. And let's have a look, increase that again. Now I can see the whole three-dimensional volume. So I think the possibilities with this new bundled pyopenvdb module are pretty limitless, and I think there's going to be a lot of add-on developers which are going to be able to make use of this. So I hope you found this quick tutorial useful, and please don't forget to like this video and subscribe to my channel if you found it useful. Thanks again, and see you next time.